Name the intervals where the function is continuous. Now, a continuous function is where I can draw a graph and not lift up my pencil or a pen or whatever. Now, wholes mean it's discontinuous. Asymptotes means it's discontinuous. Wholes, discontinuous. Filled in circle, still continuous. So I'm assuming you're -6, so we'll go with -6 right there. All the way up from negative infinity to -6, we are continuous. There's a hole there. Even though the limit exists, the fact that there's a hole there means it's no longer continuous. Then it continues, and we'll say that this asymptote's at -3. That looks like a -3 there to me. So we'll go from -6, so we'll say union. That should be -6 to -3. That was a close one. Okay, there's going to be more. And then from -3, it picks back up here all the way up until we'll say that you're 1. So -3 to +1. And then from 1 all the way till regular infinity. So we'll go with that. So again, anytime there's a hole or an asymptote, it's discontinuous. It has nothing to do, the fact that this is like concave up to concave up and it's like, not proper or something like that means absolutely nothing. So these are my 4 intervals. That's what I'm sticking with. For which of the following intervals is the function f of x equals x squared plus 2x minus 3 continuous? Now, I know what you're thinking. You're probably thinking, oh, well, let's factor this out and see if we get an x minus 3 and then cross things out and blah, blah, blah. No. Whatever we get up here, whether it's a hole or whatever, a vertical asymptote, doesn't really matter. This guy, the fact that I have an x minus 1 in the denominator means that at x equals 1, it is discontinuous. Whether it simplifies or whether it becomes a hole or whether it's a vertical asymptote, it is discontinuous at x equals 1, which means it's continuous for everything up until 1 and then from 1 on. And so the option for that is going to be B. Which of the following functions is continuous over the interval -infinity to +infinity? Now, what we are looking for is at any point, is it undefined, or at any point do I not have part of the graph? Let's take a look at the ones that I know are discontinuous. If I were to take a look at B, okay, look at the denominator. If I were to plug in 2, I would get 1 over 0 at x equals 2, which means this is going to be discontinuous at 2, so B is not an option. The graph of ln of x looks like this, because it's a log. Now, what that means is it will never, ever, 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 ever cross the y-axis here because you're not allowed to plug in negative numbers to ln of something. So all of these negative numbers is not part of my domain, which means you are not continuous. Okay? Now, there are times where 1 over sine x becomes 0. In fact, there is an infinite amount of times. If you were to plug in 0 for x, 1 over sine 0 is 0. So not only is it discontinuous at 0, it's discontinuous at 2 pi and 4 pi and -2 pi and all these other spots. So D is not continuous over the entire interval. And you might be thinking, whoa, 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 whoa. How come you said that at x minus 2 you get 2? This is really no different. Oh, it sure is different. If you're trying to find what number is x squared plus 1 going to give you 0, well, you would say x squared plus 1 equals 0. You would subtract 1 from both sides and get x squared equals -1. When you take the square root of everything, you get x equals plus or minus square root of -1, which is I. I is not a real number. So there is no real number that I can plug in here and make the bottom 0, which means this can't be undefined in any places. So A is going to be my guy. Kind of tricky there. Very bizarre problem. Find the value of a that will make the function below continuous on the interval 0 to infinity. All right, so basically what we need to do is we need to make sure that if these guys were connected, they're going to be connected at pi over 2. I don't care about 0. Don't care about 0. I need to make sure that these guys are connected at pi over 2. So in order for them to be connected at pi over 2, I need to set these guys equal to each other. Ax plus pi over 2 equals pi sine x. Now at pi over 2 is where my guys need to connect. So I need to replace every x here with pi over 2. So you become pi over 2a, right, plus pi over 2 is going to equal pi sine pi over 2. Now let's simplify a little bit. The sine of pi over 2 is 1, so the right side becomes pi times 1, right? So we have pi over 2a plus pi over 2 is now equal to pi, so pi over 2a plus pi over 2 is equal to pi. If I subtract pi over 2 from both sides to solve for a, right, minus pi over 2, pi on the right side minus pi over 2 is going to be pi over 2. So I have pi over 2a equals pi over 2. In order to get a all by itself, multiply by the reciprocal. So let's multiply both sides by 2 over pi. Magic happens. Multiply both sides by 2 over pi. The exact same magic happens, and a equals 1. So when a is 1, these guys will match up at the same exact spot and therefore be continuous. So on the left side, you have this like kind of linear guy, and then it becomes some type of sine guy, right? They connect if a is 1. If that is 1x plus pi over 2, you're good to go. These guys will be continuous. Consider the piecewise function f of x equals 5x squared minus 2 where x is greater than 1, x squared plus 2 where x is less than 1. For what value, if any, is f of x continuous? Well, 1. Why? Because 1's not included in any of these. So you basically get that guy, I don't care what it looks like, and then you get another guy, I don't care if they're connected or not. Either way, you have a hole attached to both of them at 1, so 1 is where it's continuous. Well, that was fun. Thanks for watching.